So we're going to start using all those skills that we learned previously to do the main thing that we wanted to do, was factor polynomials. Okay, we want to break apart polynomials into their multiplying pieces. Now there's a very good reason to do this, because in math allows us to see how we can break up those parts with multiplication, and in particular it allows us to see what equals 0. Okay, because if we have things that multiply to 0, we can use what we call the zero property of multiplication, meaning that if we have any number of factors, as long as if they equal 0, what we can say is any one of these factors can be equal to 0. Okay, and that will make the equation true. And that's what we want to do. We want to break these up into what we call linear factors. So the factors allow us to solve equations. Okay, it allows us to find roots of functions. Okay, so these are very important things in math, and this is the main reason why we want to do factoring. So what do we know already? Well, we know how to solve quadratics. Okay, we know how to factor second degree polynomials, and we know how to factor quadratics. So what we need to do then is, if we have higher than a second degree, like a third degree, fourth degree, fifth degree, what we have to be able to do is break these down into quadratics. Okay, so first thing we're going to do is identify how many linear factors we need. Okay, so basically what the degree of the polynomial is, and then break these down by one linear factor at a time until we get a quadratic, and then we can factor using quadratics. So for example here, this is a cubic polynomial. So we want to be able, we need to have 3 sets of brackets here of linear polynomials, linear factors. Okay, so what we need to do is, first of all, we can just guess at the first one. Okay, so we're just going to guess at the first one. We're going to use a factor theorem to be able to guess. So we know that there has to be factors of 5. Well, there's only 2 factors, 1 and 5. So we're just going to guess maybe 1 and use our remainder theorem. So we're going to plug in 1 plus 5 times 1 squared minus 1 minus 5. Yeah, that's equal to 0. There, I've got a factor. So I know that x minus 1 has to be a factor of this polynomial because it gives me a remainder of 0. Okay, so I'm just going to highlight that. That minus 1 here comes from that 1 equaling 0. So all that's left then is I just have to figure out the remaining 2 factors. Well, I know that if I break down this polynomial using the linear term and divide into there, I'm going to end up with a quadratic term. So that's what I'm going to do. I'm going to use my division. So 1, 5, negative 1, 5. I'm going to subtract. So 6. I get negative 6. 6 minus negative 6 is 5. Is that right? Oh, that should be negative 5 here. That's right. So negative 1 times 5 is negative 5. I have to get a remainder of 0. Otherwise, something went wrong somewhere. And this indicates then that my remaining quadratic is x squared plus 6x plus 5. Okay, so I know that this term here is x squared plus 6x plus 5. Well, I just need to factor this quadratic. I know how to factor it. 2 numbers that multiply to 5 and add to 6 are going to be 1 and 5. Okay, so there's my factored form of that cubic polynomial. So now if I have that same polynomial and in an equation form, I want to know when this equation is equal to 0. Well, when I have the factored form, this becomes very easy to solve because I can just say, okay, well, I have x minus 1 times x plus 1 times x plus 5 equals 0. Well, that means then either x is equal to 1 to get a 0 here, x could be negative 1 to get a 0 here, and x could be equal to negative 5 to get a 0 here. So any one of those 3 x's will give me an equation equal to 0. Now when I graph the polynomial, if I were asked to graph this, what I can then do is, well, graphing it, I know what the graph has, I at least have an idea what the graph looks like, because the factored form tells me that I have a 0 at at positive 1, negative 1, and negative 5. So negative 5, negative 1, positive 1. And what I also know is that since the leading coefficient is positive, I have to go in this direction. And we'll talk about that in a second, but basically, if the graph is going in this direction, if the leading coefficient is positive and it's an odd polynomial, it's just like a linear equation in that it has to have positive slope. So it has to be going from bottom left to top right. So what I do know about this is it's going to go something like this. It's going to go through the zeros like that. Not only that, there is one good thing about the general form. The general form does give me a y-intercept coordinate. So it gives me a coordinate here. And the only way I'm going to be able to draw this graph then is in this direction. So it has to go like this, and it's going to be drawn like that. Okay, so if I try drawing it the other way, from top left to bottom right, I run into a problem in that I can't hit my y-intercept if I do it that way. Okay, so the only way this will work is if I go in this direction. Okay, now the problem now becomes, before I could find the vertices of a quadratic fairly easily because they were right in the middle of the zeros. The one thing about cubic polynomials and beyond is that they're not necessarily, the vertices are not necessarily symmetric about the zeros anymore. So now we can't say that this 0 is in the middle and this 0 is in between negative 1 and 1. Otherwise it would be right on that y-intercept. Okay, so that's one thing that we're still stuck on. In fact, we can't resolve this problem until we do calculus. Okay, once we do calculus, then we can figure out the vertices. So now this is still an unknown. Okay, that vertex is still an unknown.